We come now to pile dynamics, which is a topic which is my specialty topic, just to be upfront about it. And it's also a topic that has mystified civil engineers for many years, and hopefully this will help shed some light. There are many foundations courses that kind of either gloss over, don't cover it altogether, or they are still stuck with the dynamic formulas, which we will see is not the way to do it overall. Talk about the background of those dynamic formulas, the development of the wave equation, how it applies to piles, the use of that in field monitoring, and Statnamic testing. Anytime we drive piles, and when we first, normally speaking, if you're driving a pile, you will, if the hammer is hammering it at a constant rate or more or less constant rate, the pile's progress into the ground slows down as you reach the end of driving. And we normally do not consider this, in terms of a velocity speed, because it's not really a continuous process. It's an incremental process. The pile advances with every blow that's placed upon it. And as a result, the way we look at this is like here. If we took, and this is the way it was done for many years, and still is in some cases, if we had a pin and that pin advanced across the front of a pile and we noted what it looked like, we would note that every blow the pile head goes down, or wherever we're measuring goes down, and then it comes back up, and then eventually it steadies out. And therefore what that signifies is the fact that in the initial impact, we are compressing the pile elastically. And that elastic compression, we talked about elastic compression of piles with Davison's method and whatnot. This is a little different because it's a dynamic process. They're related, but they're not anywhere near identical. They have, and so then the pile rebounds. Well, it's not just the elastic compression of the pile, also the soil has its own elastic and elastoplastic compression. Well, what that does is that it stores energy. It stores energy. You have energy basically in leaving out losses in the driving system itself. You've got three. You've got energy that is stored in the pile, which compresses the pile. The second is that you have energy that is stored in the soil elastically. And three, we have energy which is dissipated into the soil either from plastic or from dynamic effects. And those dynamic effects are largely due to the soil mass itself. We're going to talk about that shortly. But in any event, those are dissipated out into the soil. In simple terms, in oversimplified terms, the elastic energy in the pile and the elastic energy in the soil come back up. And we have a little rebound here. Actually, this is the rebound energy. And the net movement of the pile and the soil from one blow to the next is referred to as the set. And that's what we experience with driven piles for the most part, is that as the pile goes further into the soil, the set decreases. And that with the less set, the less energy is being dissipated into the soil, and the more that's being kicked back up into the system. And the less, obviously the less effective the energy we're using in driving is. However, it also, one of the things that people notice from the very beginning is that the lower sets indicate that there is more resistance to driving. There is more, the pile's resistance to being moved increases. And obviously at zero, if there was such a thing as zero set, and there is in some cases, virtually zero set, all the energy goes back up. And that's not a very efficient, but if you understand, if you have what people began to kind of put the pieces together and realize that if you understand how much energy, what kind of impact force goes into the pile, and then you see the set that comes back, that the lowering of the set and the increase of the driving resistance are related to each other. The question is how. And that's really the whole ultimate goal, or the first goal, not the only one. The first goal of pile dynamics is to determine people understood that there was a relationship between the two. The problem is that getting that from a qualitative sense to a quantitative sense, it was easier said than done, especially since dynamics in general were not, the dynamics of a nonlinear system like this were not well understood, say 100, 125 years ago. The first crack at fixing this problem, or trying to quantify it at least, is the dynamic formula. The dynamic formulae are based upon Newtonian impact mechanics. And you may recall this from dynamics, and I know my civil students will, in particular, will get flashbacks of dynamics, which is a topic most civils are not really fond of. And it was but basically Newtonian, it was the same type of mechanics we use, for example, in pool or billiards, when we hit the cue ball and it hits and it strikes one of the pool ball, then there is a certain amount of momentum transfer, and you got energy transfer as well, and we can use that to predict, or for example, ballistics and that sort of thing. That to apply that kind of, instinctively, I think we see that to apply that simplistic of a scenario to a complex nonlinear system like this is going to have problems, and it did. It was the first attempt to do that, and dynamic formulae actually they started back even before, in the middle of the 19th century, the middle of the 1800s, and until pretty much 1980, they pretty much ruled the roost in terms of using the hammer's performance to estimate the pile's capacity. And by the way, that's one of the advantages of driven piles, is the ability to relate the two. It's not an easy relationship, but it's one that that makes it much easier to actually know what you've got with a driven pile. We bounced through the 19th century with a number of formulas, but the one that, in American practice at least, took over and pretty much dominated for the next 100 years or so is the engineering news formula. Those of you who are familiar with publications know that one of the big ones in civil is Engineering News Record. Well, Engineering News and Engineering Record were two separate publications until they merged. And back when this was published, it was the Engineering News formula. It was devised by an American civil engineer named Arthur Mellon Wellington in 1888. One of my websites contains his full account of that. It is the most common in the American practice, and you see other formulas, the Hiley formula and all this, that, and the other in others, but for American practice, ENR is pretty much it. And it's pretty simple. Rate energy of the hammers and foot kips. S is the set of the hammer per blow in inches, as we talked about the set, and PA is the allowable capacity. I'm not going to go into the complexities of, for example, that 0.1 coefficient can vary from one to the other, the factor of safety issue with it. There's a lot of different things. And in fact, now at Wellington derived this thing empirically rather than later on people would do it analytically, or derive it. But Wellington did this mostly empirically. And he was a very effective promoter, and the formula is pretty much the standard in the U.S. by, I would say, at least the First World War. And for many years it ruled the roost in spite of its limitations. And we're going to talk about those in a minute. What it basically said, though, however, again, as you see, there is an inverse relationship between the set of the hammer per blow in inches and the capacity for a given hammer energy. And hammer energy is another thing that is subject to discussion. But it's a rate energy for the ENR formula. The set, again, and that corresponds with our qualitative field in the field. Our quantitative is a little more complicated than that. Needless to say, there were all kinds of different derivations, not just in this country, but in different parts of the world, that came up with different variations of the ENR formula, dynamic formula, excuse me. Some of them were variations of the ENR formula. The ENR formula has been tweaked and played around with over the years. But as is the case with the static capacity of piles using bearing capacity of the piles, the proliferation of methods kind of tells us that the science isn't really what it should be. And that, by the 1920s, that was becoming apparent to a few people in the civil engineering profession. So there are a lot of, to get from relating the dynamic capacity, using a dynamic method to a static method, has a lot of inherent problems in it, not the least of which is that the soil doesn't respond in the same way to static impact as does dynamic. Static loading does dynamic impact loading. You've got velocity effects, which you don't have with static loading, at least not much, because there's really no such thing as real static. All loading is in time. You've got the issues of the fact that the stress strain relationship is not the same in statics as in dynamics. One formula I'm going to mention in your book calls about is the Gates formula. It was come up by after the individual that came up with it. It is today the ENR. The only place you see ENR really, I say the only place. The one place where you see ENR, we're going to explore why that is with ENR and other dynamic formula, where you see the engineering news formula used on a regular basis is wood piling. Wood piling are more suited for dynamic formula than other types of piles for reasons we're going to discuss in a minute. But this one is the Gates formula. The FHWA recognizes this formula, and for very simple projects, very much back of the envelope type of calculations, the Gates formula is very suitable, and I use it in my own practice. And again, this is the Gates formula, and like I said, I think the FHWA was wise in gravitating to this. Obviously, if you actually use this for design, you would have to put a large factor of safety with it. But the weaknesses of the dynamic formulae were becoming very apparent, and this particular passage, and I've put it here, was taken from my own company's literature, Vulcan's literature, in the late 1930s. And Vulcan, as a manufacturer of dynamic impact pile driving equipment, was in a little bit better position to understand what that really meant than many of the civil engineers in practice. And there are a lot of qualifications that, as I said, it is not possible to devise a simple yet accurate formula of determining the load-bearing capacity of a driven pile and incorporate therein allowances for all the modifying conditions that arise. And that's probably the epitaph of dynamic formulae. There are so many different conditions, and many of them are listed here. Some of them aren't, but the ones that are significant. The biggest problem with from a theoretical basis with dynamic formulae is the fact, to put it into simple terms, is that the pile is not a billiard ball, and that the pile is not a small enough or short enough of a man to move all at once. When you strike a pile, it looks like the whole pile is moving at once, but that's not really what's going on. The pile is long and skinny, and basically, as we defined it when we first started deep foundations. And so, therefore, you have a situation where you have something else is going on, and that something else is wave propagation. And that's the first really serious drawback to dynamic formula. They do not take into account the dynamic compressibility of a pile under impact loading. And then there are others after that. We talk about the properties of the soil response and other things. But for impact pile driving, the dynamic effect, the dynamic compressibility of the pile is the number one issue in that. It was left to an Australian named David Victor Isaacs to first note this phenomenon. And the phenomenon was with wood piles, you can almost get away with with ignoring wave phenomena in piles. Concrete piles were another story. As I mentioned back a few lectures back in when we first started about driven piles, it's noted that many of the piles used outside of the U.S. are precast concrete piles, which is pretty simple. You take rebar, you put it in there, you cast the pile, and voila. The problem with this is that precast piles in particular, and concrete piles in general, don't like tension very well. And what was happening, particularly in the early stages of driving, was that piles were actually cracking about halfway in the midpoint of the pile, between the head and the toe, about right here. They were cracking. And the dynamic formulae then and now are completely incapable of anticipating this. The fact of the matter is they don't really tell you what kind of stresses you have in a pile. And so this caught the attention of Isaacs, who in 1931 published a paper in Australia which outlined his idea that was wave propagation in piles. He actually came up with a graphical machine that would allow him to model those waves and to anticipate the tension stresses in the early stages of driving. You get to layer, and I want to show you why in a minute why that happens. It was the first time. The problem with Isaac's method was that it was not an easily implemented method, not certainly at the time. There was later on in the decade, the British took on it, and one of the things that was missing in Isaac's reason was a really good instrumentation. And they actually, the Brits actually set it up under Lord Glanville to instrument using a piezometric cell at the top, at the pile head. And they also instrumented the mid and the bottom as well in like fashion. And they came up with methods which are, they kind of look like Isaac's, but they're a little bit more, but they're still complicated. They were still assuming, they were still based on the proposition of no resistance along the shaft, and they were pretty much primitive. They were complicated in computation, but they were not. They were just very elementary in terms of the way they did wave propagation. They assumed that the traditional wave equation formula applied to piles, and it does up to a point. The wave equation, as expressed here, and as you see in virtually every, most elementary textbooks and differential equations, does not include the, has no provision at all for any kind of side resistance. And of course, side resistance, as we've seen already, is elementary to piles. Piles just have it. The methods that Isaacs and Glanville were doing didn't even consider that. So the acoustics, the key though is the fact that, and both of them discovered, is right here. This is the acoustic speed in a pile, or in any elastic material for that matter, whether it's a pile or whatever. And this particular equation finds a lot of use in ultrasonic testing techniques and whatnot. It's the same concept. It's just applied differently. And it was the and it is the basically what happens is that instead of having the whole thing move as a rigid body, the piles actually, a stress wave goes from the head upon impact down to the toe and comes back. We're going to see that illustrated in just a minute. It's possible, most of you also recall differential equations, and some of you out there, I'm sitting here thinking, I'm trying not to recall differential equations. Well, that's your deal, but remember we had the string, and you had a string, usually it's rigidly supported on both ends, and you would say have an initial displacement, and then you let it go, and it would do this, and you have harmonics and all these fun things. The problem with that equation can be applied to piles on a simplistic basis. The problem is you have to take into account that most piles, except for residual stresses, and that's a whole different subject, are basically start from zero velocity. Even with residual stresses, they just don't necessarily start with zero displacement. You can use a rod, whatever. Both Isaacs and Glanville used the the undamped or simple formula for their calculations. And they used what's called D'Alembert's method to do that, which is, it's as accurate for that. If you don't have any shaft friction, it starts getting what tripped up both of them was the math of waves going up and down the pile get complicated in a hurry. So how do we make sense out of this? Well, we do it by using something called semi-infinite pile theory. And semi-infinite pile theory basically assumes that there's no pile toe. Pile goes on forever. We strike it at the top, and if we have a wave, if we're assuming undamped wave equation, just like we do, basically a wave will go down and we'll never see it again. It'll never come back and never reflect back. And if that's the case, then we can simplify the wave equation, or the wave equation is the mathematical relation between the two is interesting to this. Now you say, well, what, basically the first derivative of the displacement with respect to time over the acoustic speed is equal to the negative of the derivative of the displacement with respect to strain. Now that's interesting, isn't it? What does that tell us? Well, with a little math, basically what it does, without going into all the math, and I've got plenty of stuff on my website. If you're interested in this topic, there's plenty there to keep you entertained, bored, whatever, for a while. But basically the thing is this. If the result is that if I apply a dynamic force, a force which varies with time, at the top, at the pile head, then the velocity at the pile head and the force at the pile head are related. And basically what it over here, this is by this equation, which is in your, basically the force at the pile head with no reflections is equal to the pile impedance, which is given by this formula, which in turn is equal to the modulus elasticity times the cross-sectional area over the acoustic speed times the velocity of the pile head. The two are related. And that particular fact is important. If you have a pile with no reflections at all, then it pretty much just goes down, that's it, and everybody just looks at each other like, well, where'd that go? But piles are not semi-infinite. Piles are finite. Piles have reflections. They have reflections along the shaft. They have reflections at the toe. If we could somehow analyze the difference between what is going on in a semi-infinite pile, where we have no reflections, and what happens in a real pile where we have reflections, we might be able to relate the two together and through a series of back calculations understand how, through a long series of calculations, figure out what the static behavior of the pile is. If we can take the dynamic component out somehow, or we can account for it somehow. It's always been the holy grail in this business to take a dynamic component out, when in fact explicitly that's next to impossible. And we'll talk about that. But you have the pile, but basically if I could compare those two results somehow and figure out what the reflections mean, I could actually estimate. And that's the cornerstone of wave mechanics driven pile dynamics. One thing we can do, and it's been done in several studies, I did it for my master's thesis here at UTC, was model the pile hammer semi-infinitely. In other words, we ignore what reflections. I can estimate the response of a pile to impact without reflections, and I can find out what kind of loads are on the pile, what kind of loads are on the hammer, and that kind of thing. And basically, this is a lot more complicated than it looks. There are several cases. In some cases, for case A is pretty much the rigid ram hitting the top of the pile. You don't see this very often, not only for the pile sake, but for the hammer sake. There are a few piles that can be modeled this way, but not many. Most of the time we have some kind of cushion between the ram and the pile. We model the pile as, since Z times V, we can model it as a damper, which is kind of freaky in and of itself, but that's the way we can model it. The Z at the bottom of all four of those. What's different is that K can be modeled either without a cap, or there's also usually a driving accessory. I talked about driving accessories a few little in some of my earlier lecture. It has mass. It modulates the stress wave going into the pile. And then we have a situation where the pile cushion has its own damping because of material. Because of the pile material. You can actually take that type of data and use and actually do a closed form. I'm going to stop here, and I'm going to switch over to another piece of software to give a better. I usually use this to illustrate what wave propagation looks like, but I'm going to do a little differently this time, and you will see that the that pile you'll see that things are. You'll see what I'm talking about a little bit better. In the place of the normal things you have in the slide presentation, which are a little hard to follow, I'm going to use a program from, actually, it started in the Windows 3.1 era, and actually what you're looking at is a live running of Windows 3.1. And it's called PileWave. There's an internet version of this, but it doesn't really do a whole lot more than what this one does. Let me go through a little tour of it. Basically, the idea behind PileWave is that you are able to, on a qualitative basis, simulate wave propagation either in driven piles, the high strain, or if you're testing something like a drill shaft, low strain for defects, you can also simulate that as well. But it gives you a good idea of what wave propagation piles look like. So let's start with the base case. The base case here, we have a uniform pile, and we're going to start with a free end at the bottom. In other words, an end without any constraints on it. Something close to what you'd see in very low resistance. In other words, at the beginning of driving where there's not a lot of resistance. And let's just reduce the shaft friction, the sole friction along the shaft to a minimum. And then I hit go. And what I get, this area which is in cyan is compression, and this which is in magenta is in tension. And basically, let me go ahead and change the view to GRL just to make everybody happy. Basically, when you strike a pile or drill shafts with low or high intensity impact, you get a compressive wave going down. And it gets down to the toe. If the toe is free, it has no constraint on it at all, let's say minimal or no constraint at all, it will return as a tension wave. This is the classic problem with concrete piles. You have a situation where you go down in tension, it comes back in the beginning of driving, there's not much resistance, it comes back as a tension wave. And as you all know, concrete and tension don't like each other particularly well. And that's where your tension cracking takes place, and that's where the whole issue of pile dynamics got started, is trying to deal with tension cracking in piles. All right. Let's change the case. Let's suppose you're towards the end of driving and your toe is not moving much or not at all, and you have a fixed case. So that's the other extreme. You change that. Now notice that it comes back. It goes down in compression, but it comes back in compression. And actually, when the two waves are together, you actually get a wave doubling effect at the bottom. And that's what happens towards the end of driving. You get very high compressive stresses both going down and up the pile, which can result, if you're, for example, with steel piling, sometimes it'll reduce an accordion collapse in the pile if it's too severe. Now let's consider the effect of shaft friction. Let's go towards, say, halfway up here. And let's consider what takes place here. And then, of course, the profile is the same. And then we go like this. Notice that the program shows that we come down, but the intensity of the stress wave becomes less and less. And that's because the shaft friction along the pile attenuates that. In other words, as the stress wave goes down, it mobilizes the resistance along and basically dissipates energy through the shaft into the soil. So by the time it gets down to the toe, you've got less intensity in the stress wave. The stresses are dropping, the force is dropping, and that also happens when you go up. So that, for driven piles, that's very much, and then if you get a lot of friction along the shaft, basically the wave will all but disappear by the time you come back. So that's pretty much for nice uniform piles. Well, what happens if piles are not nice and uniform? Well, this program also shows how that happens. First, let's consider the case of like a wood pile. And we'll see if we can get like that. Well, it's conical, where it's not evenly shaped. The nice thing about it is if you change the shape, it shows you right here on the side. And then we're going to put the shaft friction down. Let's start with no shaft friction. Still a fixed end though. So you notice that along the wood pile you get reflections. All kinds of continuous reflections along from the shaft. And basically what this is that for tapered piles, you have a situation where the shaft, your area, cross-section area is constantly decreasing. You're getting a constant stream of reflections coming back. We can also see how that works with a free toe in the early stages of driving, and we get this kind of thing. So tapered piles, how important this is depends entirely on how much the pile is tapered. If its taper is fairly minimal, it's not that important. If the more taper you have, obviously the more you will see this type of effect. You're getting a constant return to the surface of the stress wave as the pile. Now, let's look at another case. And let's go into their fancy little library. Let's go to the wireframe, make it look a little nicer. Library. Let's say that we have let's see what we got here. Let's say a small defect. Let's say it's a small defect. Let's say that at one point, this is particular, like for example, we have a pile crack. What will happen? Well, let's go. We've still got a free end. Maybe we ought to fix the end. Because normally we would test something like this at the end of driving. So we do this. Notice how at the crack you get a lot of return stress waves. If you and basically if you're doing this, particularly like in a pile integrity test, a PIT or something like that, you're actually returning the stress waves to the top. You can actually determine where defects like this are based upon the return pattern. And you see this return pattern here. You've got both tension and compression waves returning to the surface, and they will pick that up, and using the signal processing capabilities of whatever software you're using to process this, it will give you an idea of where this defect is. Let's try something else. Again, the lib is very handy. I could make up stuff. You can actually shape the pile pretty much the way you want to with this. Let's suppose we have a bell shaft. Let's see what that does. And again, something like that. everything is hunky-dory, you get towards the bottom, and then things get very confused. Where you start getting many different types of reflections from the bell shaft. And that was the so that shows you what will happen when you have a bell shaft. Let's try something else. Again, the library. Let's look at a defect in the drill shaft, similar to what we get with, we got all kinds of defects here. They give you a nice selection of defects. Let's say that we have a drill shaft. Well, actually what I can do is you remember we had an hourglass type of thing. Yeah, you remember there was an hourglass. In other words, the drill shaft looked something like that. You remember we had whether you had the rebar sticking out and all that fun stuff. What would you get with that? Well, what you get is this. If you get a drill shaft, for example, that has a continuously taper, you get the same problem you have with wood piles. You're going to get a lot of different reflections back to the surface. And then about here in the middle, you get major return. You get all of a sudden you start getting different transmissions of the compression wave and different reflections. And then, so therefore, this is a very kind of confused pattern because you're dealing with a non-uniform cross-section. And if you throw in the effects of rebar, then you're going to get a very complicated, and you use your software to reduce this data and find out where your defect is, what's the nature of the defect. The ability to do this for both driven piles and drill shafts, the ability to analyze them, to use the stress wave, not only to determine, say, for example, the capacity of the pile, like we do with the case method or cap web, but also determine the integrity of the pile, like we do with PIT. They're really kind of two sides of the same coin, and that ability is crucial, absolutely crucial in being able to analyze what's going on with deep foundations without having to dig them back out of the ground again. So this is a quick overview of what wave propagation looks like. Like I said, this particular piece of software is now on the internet and is available to you to play with, and I strongly suggest that you do so. I'll furnish a link to that. And also, it's also kind of fun to look at. This is actually a Windows 3.1 implementation, and you're actually seeing the way it would look in computers 35, 40 years ago. So, well, not 35, 25 to 30 years ago. So in any event, that's pretty much this quick introduction to wave propagation piles. This is a good way for you to see how that works. And we'll now return back to the slide presentation. World War II put a serious interruption to much of the research on pile dynamics, but by the by the end of that tragic experience in the late 1940s and early 50s, it was obvious that the solutions that Glanville and Isaacs and all of them had proposed were really not only not suitable for practical application, but they didn't really take into account all of the complexities and the nonlinearities and whatnot of real driven piles. The first major effort to change that and to actually shift from closed form solutions to numerical method was done by Raymond Concrete Piles, E.A.L. Smith, who was their chief mechanical engineer. And he worked Raymond was headquartered at the time in New York. They didn't move to Houston until, I'm thinking it was sometime in the early 1970s when they did. But the time they were in New York, and IBM was out on Long Island, and Smith worked with IBM. He worked with some of the pioneers like Milne of numerical analysis, and came up in 1960. Published. Actually, he didn't publish the paper that made him famous. It wasn't published until he retired, and came up with the original paper and the original numerical method. In the beginning, the solutions were done manually. We're talking about a computer solution, basically a room full of people, actually, doing this computation, then handing it off to somebody else, and they do that, and they hand it off. And with a one-dimensional system like this one, it's a little easier to do. I wouldn't try it. Well, of course, today we don't have to try anything like that. We have more. There's far more computing power in this iPhone I'm talking at than there is that Smith ever dreamed of having in his in his wave equation solution. It was one of the first applications of computers to civil engineering. And in that respect, the wave equation for piles is a pioneering effort. Once Smith's solution hit the street, basically, it became obvious to many people, especially in the government, that this was really the way to go. The question was how to convince the civil engineering profession and all of the states and the federal agencies and whatnot to adopt it. The first solution that after Smith that really gained currency was the TTI solution, which was the Texas Transportation Institute at Texas A&M University, and it was done in the late 1960s. It was very similar to Smith's solution, and actually the code for that is on my. See the code. I think the code is there, but definitely an executable is on my website. Its biggest another, in addition to the feds pushing this, another group of people that were pushing it very hard. One reason why I ended up at Texas A&M was the oil industry. The oil industry was driving very long piles, and dynamic formulae weren't anywhere even in the ballpark on those. The piles were just too long. Basically, what you would do is you would hit the specialist stuff driven from the surface, where you would basically put impact pulse up here, and down here it interacted with soil, so that it basically decoupled the two to some degree. And the wave equation was not was absolute necessity for those. I know that those were the two people behind that. Many of them have passed on. I know Lee Lowry is still living and teaching at Texas A&M as of this recording, as far as I know. The individuals that really, however, there were two things that were missing from the TTI solution, two major building blocks. One of them is the modeling of the diesel hammers, which were becoming more popular, particularly for onshore applications. And the other one was an inverse method. In other words, you could take the wave equation, you could play around, and you can still do it this way, play around until you get something that looks like it's, if you had data from the field, you could take the wave equation and play around with it. That's not necessarily the best way to do this. The individual that, the two individuals, actually there's three, who probably had more to do with actually making those two modifications started with George Goebel, who was at Case Western University up in Ohio. and his graduate student and later partner, Frank Rauscher, and also Garland Likens coming on a little bit later. And the three of them particularly and were the ones that developed the GRL weep, which included the diesel hammer, which is diesel combustion, and interaction with the pilot itself is complicated. And they had some other convenience features so that it wouldn't be so hard to run the wave equation program. Their efforts, and along with the usual educational program, and their efforts have resulted, finally got the wave equation established as a viable methodology. And in the process, it also moved our understanding of installation-driven piles forward. It was not easy. Of the three of them, George was the most, who has since passed on. The other two are still with us. George was very forthright in his efforts to get it accepted. And as I've said before, if you have a new technique, it takes an enormous amount of, because it's part salesmanship, it's part technical presentation to get it accepted. Our normal, the normal, default is always do it the way we've always done it. And in some cases, that's the way to do it. But when you've got manifest defects, it's not. TNO represents is the Dutch organization, and they developed the wave equation in Europe. They use the method of characteristics. It's a little different numerical technique than Smith or TTR or GRL used, who used a lump mass system, a lump mass solution. I've gone into a lot of methods and I've kind of mentioned some of them in passing. Why the numerical solutions are necessary. The bottom line is that pile driving is a highly nonlinear phenomenon, and has a lot of nonlinearities, and, for example, inextensibility in the system. You have to model the system in such a way, for example, that the RAM only puts the hammer cushion in compression. It cannot be in tension. It just can't be. With the complexities of the diesel hammers and other constructions, and of course you get into cushionless hammers, and that's another issue altogether. All of these forced the use of numerical methods. And numerical methods are, when we talk about the wave equation today and with driven piles and other things, we're almost inevitably talking about a numerical method. In practical, this is a good summary. You basically divide the system up into masses and springs with dashpots representing velocity, energy dissipation, and the springs for the sole are elastic perfectly plastic. The spring for the camera cushion takes into account losses using a coefficient of restitution system, and you set the system up and you run it, and you get results, and you look at them. Please look at them, and then if you have to run them again, you do, until you get a solution which you believe to be the best solution to the system you have. There are two. This is the most important. And there's a lot of different ways of interpreting the data, and the newer versions of GRL is continually improved WEAP until we've got this. There are many different outputs. This is the bearing graph, and this is important because your TAM wave program basically has this as, puts out a version of this. There are three things that you get out of this. The first is the blow count versus the ultimate capacity, the one at the bottom. You'll notice in this case that it comes up and then it flattens out. Obviously, you reach a point where just beating on the pile you get a diminishing returns effect where just beating on the pile, basically you run out of, it just doesn't do any good. In addition, it damages the hammer of the pile. We normally have, to deal with this, we normally have a blow count criterion where we say that, well, we want 120 blows per foot, which I know is traditional for the Vulcan hammers. Sometimes you'll get 240 blows a foot for other types, and some DOTs do that. But you get a point where, it's time to call a halt to driving when we get to that. In offshore, you could get much higher blow counts even than that, for a variety of reasons. The second thing is compressive stress. Obviously, we don't want to over compressive stress the pile. And the wave equation is capable of estimating the maximum compressive stress in the pile during driving, and that is up here. For this particular case, this is an offshore type of pile, and like I said, offshore piles, the top and the bottom tend to be decoupled, so the compressive stresses are not as influenced by the blow count. In many piles, the higher the blow count, higher compressive stresses. The interesting one always is this one, which is the tension stresses. Now, the tension stresses are much lower than the compressive stresses. In early driving, as you saw with the pile wave demonstration, you get tension stresses coming back up from the pile toe. And with concrete piles, those are very important to monitor. In fact, what we normally do with a concrete pile is we start out with a lower energy and then increase the energy once we get past that initial very loose phase where you've got very low blow counts or high sets. And blow count and set, by the way, are inverse. I should have mentioned this sooner. Blow count and sets are inverse of each other. I believe your book deals with that. Those are the three big things in a bearing craft. You've got other ways that you can drivability analysis, but basically this is the most important. So you say, well, you get these stresses. How do I know that they're not too much? This is how you know they're not too much. This is the AASHTO allowable stresses and axial stress driven piles. Now, important to note, there are two maximum stresses. You have design stresses, which is the stress you permit after you finish construction and put whatever you're going to put on top of it. Driving stresses are during installation. That's when you see driving stresses. And driving stresses are given for concrete piles, for steel pipe, concrete filled steel pipe piles. Basically, what you do is you drive as I mentioned earlier, that or even a mandrel-driven pile is the same way. You drive the pile first, and then you put the concrete in. Basically, you're driving a hole in the ground to put concrete in, and that's what you're doing with those particular types. There has not been a publicly released version of GRL WEEP since the late 80s. And it's a DOS program. Yeah, it's on my website too if you're interested. The program that I'm going to ask you to use was the TAMWAVE program, which I actually came up with in 2005 and have modified it since. It allows for axial load deflection analyses, and if you want lateral load deflection analyses, and wave equation drivability. It does it all in one shot. It has its tutorial. It's got a very detailed tutorial on how to use it. It's on my website. I may, like I said, may put a video for it. I've talked about the program earlier, but now we can go through the whole thing to the end. It uses the LP method for the axial load deflection and the CLM2 for the lateral load. It has a hammer database and gives an initial guess as to what kind of hammer you might want to use. Just because it says that doesn't mean that that's the hammer you should use. You may find that the blow counts are unacceptable. And includes an estimate of soil setup and clays. The 16-inch concrete pile example is we've talked about this earlier. This is the general output for the wave equation analysis, along with a hammer Vulcan 030 that it recommends to use to drive. The reason why it recommends that, and I'll show you why in just a minute, it probably recommended a smaller one. I had to upsize it. This is the force time output. Notice that, and this is important, that the blue line is the pile head force, and the red line is the pile head impedance times the velocity. You're going to see that again when we get to cap weapon analysis. But those are the two things that it gives you. The 16-inch concrete pile example. Let me back up. The reference capacity, the soil resistance, the SRD, is in kips at 637.8, and 637.8 is the point at which you want the blows per foot of penetration. Normally, for the hammers that are in there, 120 blows a foot is the maximum you want to do in your drivability studies. You want to basically increase the size of the hammer to the point where the blow count is as close to 120 as possible without going over, and the stresses are at an acceptable level, both tension and compression. And in fact, it gives you both maximum tensile stresses and maximum compressive stresses. And you use that table I presented earlier, which is this one, to see if that's the case. The results of, now this bearing graph is what you're going to get out of TamWave. It gives you this chart. It gives you a nice table. The table can be taken, copied and pasted into a spreadsheet, and then you can plot this. Notice that the blue is the soil resistance, and as you come up, you have, again, it's a diminishing returns. It starts here, it comes up. By the time you get to the 120 blows a foot here, you're running about, upper 600s, which is good. You've got this magenta line here, which is the maximum compressive stress. It increases some and then levels off. It gets to the point where it's basically a function of what the hammer is, the force induced by the hammer and impact. And then, without consideration of the pile movement. And then the tension force in the lower reaches, it's higher, and then it comes down almost to zero. Once you get past the initial driving, concrete stresses frequently become very low. And that's basically what you do for a wave equation analysis. TamWave eliminates a lot of the steps. For example, these are the basic steps in your book. I think goes through these. The hammer type, suggested trial energy in the chart below. The program includes that, by the way. And the pile, and by the way, the database for is an ascending energy order. In other words, as the energy increases, so if you get a hammer that's too small, you just increase it. You just go down in database down, and with increasing hammer size. Pile data, you input that into TamWave in the beginning. Soil data, put that, it's simplified in TamWave. You construct the analysis. The setup factor is done for you. You run the stack capacity. TamWave does that for you. You input the data for the hammer. You've got a database for that. Then you run the program, and then you analyze the results. One important, again, and I kind of mentioned this before, these are kind of a review. Soil resistance to driving is an important concept. And many times, the driving resistance of the soil and the soil you actually have is not the same. And in this particular example, there are a couple of reasons. One of them is scour. You will if you've got soil that you're driving through to get the pile in the ground initially, and then you anticipate that that soil will go away or might go away and scour, you don't want to exclude that soil because, for drivability, because it's there now and you have to deal with it. Later on, you may not be able to count on it. But for now, you have to count on it, and therefore that goes as part of your driving analysis. In addition to scour, the other major, another major factor, and TamWave actually takes this into consideration, is soil setup or relaxation, depending on how you look at it. Basically, if we talked about this in static load testing, where I talked about you drive a pile at the EO and the end of initial driving, you stop, you take your dynamic measurements from that, but then you let the pile sit. And then you might restrike the pile, and then you might run a static load test. Why? Because generally speaking, at the second time, you will have a higher resistance after the dissipation of pore water pressures and rearrangement of the particles and whatnot than you will at the end of the initial driving. So the clays tend to give you an SRD which is below the which is actually below the the resistance the soil will experience during the actual use of the foundation. And I talked about pile setup before. We've talked about it, and it's no different. And they have this pile resistance example that goes into that. Again, this is review from earlier, but now that we're actually into dynamic testing, I think we can get a little bit better perspective about what's actually going on with this. I've talked about end of initial driving and restrikes and all that, and obvious it should be, well, I'm not going to say it's obvious, but it's implied that somewhere in there are some some instrumentation or some kind of data gathering. I talked about at the beginning of this lecture the rather primitive blow count thing we used to do. What we do now in terms of, we still take blow counts. Now, there's no question. I mean, usually they will, if this pile advances a foot, they count the number of blows on it, blows per foot. Set is 1 over per foot is 1 over blows per foot. Or this number of blows in an inch, blows per inch is 1 over that. Normally with dynamic testing, we have the load is the impact force of the ram applies a load, as opposed to what we do with static load testing. Force is measured by strain gauges. Velocity is measured by accelerometers. And then, of course, the accelerometers, you integrate that, you get velocity. So it's not a direct measurement of velocity. This force and velocity time data is used to estimate the static pile capacity, pile and monitor stresses during driving, and that's and then that data is taken. Well, I'm getting ahead of myself. Pile driving analyzer. Once you get all this data going into a pile driving analyzer, now of course they've got where you can gather it in the field, transmit it to the office. Somebody sitting in the office watching all this and gathering the data in the office. And you can devise stresses, the hammer performance. You can also do pile integrity, which I think you saw that in the pile wave demonstration. For a dynamic load test, the bearing capacity at the time of the testing. Now, I've got something in there which deserves a better explanation. Separating dynamic from total static plus dynamic soil resistance. I think it's fair to say that we don't explicitly do that. With the case method we do, and we're going to talk about the case method in just a minute. But normally what we try to do is we try to match up what we ultimately do with CAPWAP-C is we match up the data we get from the pile head, and we model the pile, and we try to eventually, through an iterative process, match up the data, the data of the that we have with the response of the pile. In other words, we want to get to the point where the response of the pile matches the data that we're taking. And normally with CAPWAP, they take the velocity and try to match the force. In my research, I did the all the way around. It doesn't really make any difference one way or the other. That's how you do it, instead of explicitly trying to split. I think in the early years we tried to explicitly split the two, and it was a little complicated with the case method. We actually do that. You get from pile driving analyzer, you get data looks like that. That's an actual data taken from an actual pile analyzer. You get force time, velocity time. Now, this is where panic ensues. Very frequently with students who are not familiar with this. You'll notice that this is in kips. Kips is a unit of force. This is in milliseconds or L over C. Milliseconds is a measure of time. L over C is a dimensionless. L over C represents the time it takes for a stress wave to get from the top head of the pile to the toe of the pile. 2L over C is a round trip. Normally, the kick we get back from the toe takes 2L over C to get from here down here, then it impacts the toe, and it comes back up L over C. You get 2L over C. And that's very important when we get to the case method. But that is a complete round trip. And traditionally we measure, this can be either in milliseconds or L over C. L over C is more convenient, or both, as you see in this case. Like I said, this came from an actual CAPWAP analysis. The force time is the solid line, and the velocity is time. But now wait a minute. How do I plot velocity on a y-axis that's in force? It's simple. You recall that for semi-infinite pile theory, that force is equal to the impedance times the velocity. So what I do to essentially match the two up is I take the force, I take the velocity trace, I multiply every point times impedance, and I get it where it matches up with this force. This is not really V, this is Z times V. That's important to note. Now you will also note that in the initial impact, they're the same. And that's very common. Especially we get with steel pile, it's very, very common that they be identical. And in many cases they are identical. But as the pile proceeds, as the stress wave, they separate. They're different. basically what I do to get an idea of the SRD is I basically compare. Basically, actually, I talked about the model lining velocity, and trying to. Is I keep changing the model below this thing. Let me just go ahead and do this. This shows you a schematic of how it's done. I believe this is in your book. You've got this. You set this up in the computer as a model with the springs and the dash spots and all that. And basically, you start down here where they're different, and you in this case, this is typical CapWAP, where you take the you input the velocity at the head, or the velocity times the force, and then you try to get the forces to force. These are two forces. The initial model are very different, but as you get to close to it, the two forces should be the same. In other words, given the same velocity time history, we get a force history. I did it backwards from that. And I'm not saying that's superior because it just doesn't really make any difference which way you go. It depends on what kind of computer model, which mine was fairly different from theirs. And that's how you keep making. It's an iterative process where you make changes all the time. This little thing, MQ, is called the match quality. As you approach perfect match, which you don't get, match quality goes down. You want to get it down as low as you can. Those of you who had me in fluid mechanics lab will recall I talked about one norm optimization. There it is in all its glory. It's a type of one norm optimization. Okay. Case method for pile analysis. When we first started this adventure in the early 1970s, Goebel and his colleagues, I think, really wanted to come up with a simple and easy to use method to take into account dynamic effects and to get static effects back. And the method they came up with is the case method. The case method is not used as much today as it has been in the past. My assessment of the case method is this. It is it's nice little back of the envelope method for estimating that. There are some theoretical issues with the case method, which I'm going to talk about. And the case method is, and it can be used in some situations for job site control. It is not it is good as an academic exercise because it's fairly easy to apply. It's good to teach people how pile dynamics basically works. But if I'm on a job, I'm going to use something like a CapWAP or some type of method that actually does signal matching. But we're going to talk about the case method. Definitions. There are two times we have to, and it assumes that the pile resistance is contrary to the pile. That's the first problem with the case method. It's not. Some piles it is, but a lot of piles it isn't. The static toe resistance is completely plastic. Second problem. There is some elasticity in the pile toe resistance, as the wave equation models it and this CapWAP C models it. So, with that in mind, with those limitations in mind, those disclaimers up front, let's continue. Uses the output from the pile analyzer. Definitions. T1 is the peak impact force. In other words, if I'm using, I'll go back to this. T1 is right here. We're the first peak impact force. T2 is T1 plus time 2L over C. And 2 over C can be expressed if T1 is in 2 over C is in milliseconds, and T2 is T1 plus that millisecond, or however you want to do it. F1 is the pile head force at time 1. F2 is the pile head force at times 2. V1 is the pile head velocity at time T1, and V2 is the pile head velocity at time T2. You read all these off with a graph, as you'll see. Z is the pile newtons. is in pile impedance. ZV1 is the product of the impedance and the velocity at time t1. ZV2 is the product of impedance at time t2. RTL is the total resistance, static and dynamic. This is where the case method explicitly separates the dynamic resistance from the static resistance, or at least it attempts to. RS is the static resistance, which is what you're interested in for most applications. And then RD is the dynamic resistance. You'll know that the total resistance is the sum of the static resistance and the dynamic resistance. The total resistance is given by that formula there, and the dynamic resistance is given by the next formula. I'm not going to go into all the derivation of it. And then the static resistance is equal to the total resistance minus the dynamic resistance. I've taught this a little differently in the past. The results are the same. Hopefully it'll be a little less confusing. Interpretation methods. Just like static load testing, the dynamic load testing has interpretation issues. First, let me get this out of the way while I'm thinking about it. In CapWAP, what they do is once they've got the pile modeled, they run a static load testing on the model. And they interpret that according to the Davis method. They could just interpret according to another one. Another method could use that. There are two methods that we're going to talk about interpret. And CapWAP, case method has its own interpretation methods. First, RSP method. The T1 for the RSP method is the first peak force in the force time curve, as below. In other words, you have this is point 1, point 2, and surprisingly, FT1 and ZV are the same. So you see here that you've got both, in this case, you've got a scale for force and velocity. And this point is the same. And they're related between each other by the impedance. The second point is F here and VT down here at 2L over C. We simply come up, we take those data, and that's how we figure those. RMX method is a little different. RMX method starts 30 milliseconds after the peak, and then 2L over C is 2L over C after that. So in other words, instead of picking this time and this time, it goes 30 milliseconds forward, picks this time and this time, which I guess is a good reason why we have why we like to have both milliseconds and 2L over C in our time scale. It depends which one you use, or there's other methods as well. Depends entirely on the type of pile you have. So a case method example of this force time here, and you'll be given, by the way, forget about tables of numbers. This is pretty much what you're going to have to work with. Find the case method using the RSP and RMX methods. So what do? I start with this. I scale this up. I will try to give you a better scale, just as a disclaimer. I'll try to give you a better scale on this side. F1 is 1406 kilonewtons. F2 is 8. You're reading it right off the graph at the two different times. V1, 3.93 meters per second, and ZV1 is the the impedance is 381 kilonewton seconds per meter. How do I know that? What I did was I took this, I divided it by that velocity, and I got the impedance. ZV1 is equal to 1497.33, V2 is 1.07, and ZV2 is 407.67 kilonewtons. So now I've got all my, and by the way, you'll note that I put the formulas for these in ZV1 and ZV2. It's a little simpler that way, a little simpler. to put it in those terms than to put z times v1 minus v2 or whatever. RSP method, I'm going to assume j is equal to 0.4. I'm going to talk about that assumption in just a minute. RTL is equal to just plug and chug. And you get 16.97 kilonewtons for my total resistance. RD is plug and chug again, 514. Subtract the 2, I get 1183 kilonewtons. The RMX method is the only thing different about it is the data points. So I picked the 2 data points. I picked the values off the graph in the same way I did before. And I've got now F1, F2, and ZV1 and ZV2. I'm going to, because it is the RMX method, I'm going to assume that J is equal to 0.7. By the way, if I give you a problem, I'm going to tell you what case method I want, J constant I want. And we, again, plug and chug all the way. We get almost no dynamic resistance in this, and I get a different result. If, however, you have to determine the case damping constant, these are typical values. In the reality, and this is where something a lot of people don't appreciate about the case method, is that the case method is a job-specific quantity, which can and will change with changes of soil pile, even pile hammer. It can be used it's job-specific, in other words. So these are nice ranges that we have. They've changed over the years from here to here. They need to be calibrated for a specific job. And this isn't nice for preliminary, but if you're going to actually use it, and it's not used as much as it has been in the past, then you will need to specifically calibrate for your job. Kind of a general, this, for example, is with a very strong toe resistance and minimal shaft resistance. With minimal resistance or toe, you do get this kick at the toe. You'll notice that the stress wave comes back up in tension, and it gives you this kick. With a large toe resistance, you get something like this, where you get that wave doubling effect we talked about in the pile wave demonstration. And last but not least, with large shaft resistance, the toe resistance gets wiped out. Again, this is an easier thing to understand if you look at it from the pile wave program demonstration I gave you. Dynamic pile testing is quick and inexpensive. It can test all types of preformed piles. No special preparation of the pile other than sticking the accelerometers and strain gauges on it. The stack attack capacity is interpreted, and it does require experience for correct interpretation. Quite a bit of it, in fact. The last topic I want to talk about is Statnamic testing. I want to draw a personal reminiscence to start this thing. And it goes back to 1980. In 1980, it was in March, I took a trip to Canada. It was my first trip up there. And I went to Hamilton, Ontario to visit the Birmingham organization. We were talking about actually doing some mutual business together. And I got to meet really fine people. One of those was Manny Fine, who passed away last year. And he was one of the people. He actually was executive director of DFI for quite a while, for the D Foundations Institute. But the other people, of course, were the principals of the company, Bill Birmingham and his wife Lou. And the Birminghams had been contractors on the lakes since the 1890s, I think it was. About as long as Vulcan had been out there putting pile driving equipment. On Lake Michigan, they were on Lake Ontario. So they had gotten into the equipment business, and they were producing a diesel hammer at the time. They went on with their leaders and other types of equipment. And both of us were, both Birmingham and Vulcan were long-term family businesses, and we were talking about some of the aspects of that. And he was talking about his children, and one of them, much to Bill's kind of disappointment at the time, was going to art school. Well, the art school student was Patrick, and he ended up a principal in the business. So Patrick set his mind to do the work and did well. And one of the things he noticed in going to conferences and whatnot is that this is DFI conferences and all those, is the fact that geotech engineers would get up and talking about mobilizing the shaft resistance and mobilizing the toe resistance. And Patrick, in common with I think a lot of us, verbalized, it finally hit Patrick that, there's nothing moving. Or at least not, compared to somebody who is in impact pile driving, there's nothing moving. Everybody, it doesn't look like anything's moving here. So Patrick decides that it's time to change that, particularly with load testing. And what he came up with was the Statnamic test. The Statnamic test is sort of, the thing that load testing, the thing that varies across different types of load testing is the rate of loading. On the one end, you've got a static load test, which is slow. On the other hand, you've got high strain dynamic test, which I've been talking with this whole time, and it's very fast. Statnamic test falls somewhere in the middle of that. And that is what Statnamic testing is all about. And the basic principle of it is very simple. It has a controlled explosion. I know that Birmingham's people get very nervous when it's referred to as an explosion. Well, it's a controlled combustion. Let's just put it that way. It loads the pile for a longer time than high strain dynamic testing we've been talking about. The problem with any static load testing, or any load testing period, with impact load testing you can kind of ignore this, but with this test, every static system has a reaction system. So what kind of reaction system do you have for Statnamic? You have a system of weights. And basically what happens is that when you have this nice controlled explosion, the pile goes one way and the weights go another. And you have a sensor to record the deflections in the load cell, which is in there, like you have with static load testing, records the loads. And you get, the result is that the load deflection curve, you get two different load deflection curves in Statnamic. Well, then once you get those, you take those and you process those into a simulated static load test. You do that with dynamic testing as well. And you've got a static force, and you've got, you get a static force here out of it. You get total force, the inertial force, and then a static force out of that. And so you're able to do a load test that comes closer to being a static load test, to a static load test than dynamic testing does, without the lengthy, without the lengthy process of a static load test. The advantage of the test is it's much faster. It does not require a pile hammer as high strain testing does. And it's especially applicable to drill shafts and other bored piles. The rate of loading is lower, and it reduces the possibility of damage. It does not give a clear picture of the distribution of capacity between the shaft and the toe. I think that's a problem, as is the case with static load testing, that could be beat. And it's not entirely developed, although there's been advances continually with statnamic testing for clay high dampening soils. I would strongly suggest, if you're in a job site situation where nobody is really, it's an excellent method. It has its limitations like any other method, but it combines characteristics of both static testing and dynamic testing into one. And it can, of course, be used, I mentioned about lateral loads. It can be used to simulate impact loads as well, particularly in lateral loads. So that, in a nutshell, is pile dynamics. It's a very widely varied subject, but we've reached the end of the section on deep foundations. So until next time, thanks for watching, and God bless.